I've been talking about power series. So this is really the next major idea in the development of calculus after the fundamental theorem of calculus. So let me remind you of the main theorem that I wrote down last time. So we've got a power series. So that's just the data of this infinite sequence of coefficients, which gives you this infinite sum of these a(n) x to the n's, this infinite sum of monomials. So that power series defines a function f of x on domain, well, the x is every x for which that infinite series converges. And the big theorem about power series tells you that a power series has something called radius of convergence r. So this is a real number greater than or equal to 0, or it's also allowed to be the symbol infinity. And is characterized by two properties. The series converges for absolute value x less than r, and the series diverges for absolute value x bigger than r. If the absolute value of x equals r, it may either converge or diverge, depends, there's no information here. But that means that on the open interval from minus r to r, inside the radius of convergence, the function is defined. And the theorem goes on to say that actually on that domain, the function is differentiable with derivative equal to what I call the term-by-term derivative of that series. And that term-by-term series also converges on this open interval minus r. Okay, so that's kind of the fundamental theorem about power series. Oh, I should write down one more property. Providing r is bigger than 0, so that it's differentiable about 0, you can recover the coefficient an from the function, because an is the nth derivative of the function at 0 divided by n factorial. So that's kind of an important little fact. Let's put a box around that because it's useful. Okay, so power series. So the idea, which I started to kind of convince you of last time, is that if you have a differential equation, should be thought of as a sort of a recursive recipe for computing a power series. And I tried to explain what I meant already with the nicest possible differential equation, namely that f prime equals f, with the initial condition that f of 0 equals 0. So in that case, using this formula, if you assume that f of x is defined by a power series, you work out what the power series has to be. an has to be 1 over n factorial, and so your function has to be equal to the power series sum as n goes from 0 to infinity x to the n over n factorial, which of course you recognize that's our e to the x power series. So then this power series becomes the original definition of the exponential function. So we sort of discovered this by thinking about the differential equation we wanted the exponential function to satisfy, and that recursive recipe given from that differential equation told us what power series we should think about. And then you turn it on its end and you take that power series as your very definition of the function e to the x. You have to do a little bit of stuff. You have to use the ratio test to prove that the radius of convergence of that power series is infinity. So this function e to the x defined by that series has domain the entire real line. And this gives a function which does satisfy the differential equation. Right, so using this property here, this power series, you can differentiate it, and the nice property of that series is that the term-by-term derivative is just the same power series back again. And in this way, you construct a solution of that differential equation with that initial condition. And we already knew that if there was a solution, it was unique. It was just that starting from the differential equation, we didn't really know how to prove existence of a solution. This power series method gives you an easy, nice, clean way of constructing the solution to that equation in the first place. So that becomes, I think, the best possible definition of the exponential function, the best rigorous mathematical definition, that is. And you're in business, because with this differential equation is a nice way of working with this function and proving properties about it. I talked already, I think, about the law of exponents. E to the x, e to the y is e to the x plus y. I showed you already a couple of proofs of this. In fact, I showed you one way to prove this, starting from our original definition of the exponential function as being inverse to natural log. And so one way to prove this was by using laws of logs, and we went through that. But now I think that really we should forget that definition of the exponential function as inverse to natural log, and we should start again and use this power series as our preferred definition for exponential function. But this preferred definition gives you a solution of this differential equation, and I showed you how to use this differential equation to prove that law of exponents, and that's probably the easiest proof. But I want to just kind of quickly show you a third way, because maybe it's the most natural proof, although it's not necessarily the easiest. I'm really doing this because it gives me a chance to just show you a little bit more of the sort of tricks that you play with power series that I want to have in place at this point. So here I'm just using the very definition. E to the x by definition now is that power series. 1 plus x squared over 2 factorial and so on. E to the y by definition is that power series. And what I want to do is I want to just FOIL out these two brackets. So I just want to distribute them out. And, well, you have to think about what this means. If they were finite sums, then of course you can do it. But they're infinite sums. So you always have to be rather careful. It needs to be justified. So this is justified by the theory of power series. It depends on the absolute convergence. So I forgot to write that back here. Not only does the function converge inside the radius of convergence, it actually converges absolutely inside the radius of convergence. And that's a key theoretical property that justifies all of the manipulations that you like to do with these infinite series. You can basically treat them as though they're finite sums because of absolute convergence. So this justifies my foiling it out. So I'm just going to take the first terms, 1 and 1. And then I'm going to take the degree 1 terms. I'm going to take the x and the 1 and the 1 and the y. And I'm going to take the degree 2 terms, the x squared, the x and the y squared. And then I'm going to take degree 3. So you kind of see the idea. What have I got? I've got x squared over 2 factorial, which is going to hit the y, and x is going to hit the y squared over 2 factorial, and then y cubed over 3 factorial, and it carries on like this. So what I'm really forming, I'm kind of ordering these terms in order of degree. I'm forming what's often called the Cauchy product. So it's a sort of common sense construction. And there's some theory behind this which justifies that this makes sense, and the new series does indeed converge. So what have we got? Let me just rewrite it a little bit. If I pull out a 2 factorial, I've got x squared plus 2xy plus y squared. If I pull out a 3 factorial, I've got x cubed plus 3x squared y plus 3xy squared plus y cubed, and so on. And you probably recognize this. Here I've got coefficients 1, 2, 1, which is that second row of Pascal's triangle for the expansion of x plus y all squared. And then here I've got coefficients 1, 3, 3, 1, which is the third row of Pascal's triangle from the expansion of x plus y all cubed, and so on. And so lo and behold, what I have here is the definition of e to the power x plus y by our power series definition. So that proves laws of exponents kind of directly from this definition. Okay, so I think that's the best way of defining the exponential function using that power series. Let's just, before we kind of go too far, what about natural log? Could we define that by power series? I already showed you a definition of this, right? I showed you that natural log of x, you could define it as an integral. So that was the definition that we used last time, the rigorous mathematical definition of natural log. But maybe power series are better. So let's think what would happen if we try to define natural log using power series. Well, the first issue is that actually x equals 0 isn't in the domain of natural log. I only ever want to talk about power series centered around the origin. So let me not do natural log. Let me shift. Let me do natural log 1 plus x. So it's defined at 0. So let's see, what can we say about this function? Well, the derivative is 1 over 1 plus x. And what's f of 0? F of 0 is natural log of 1, which is 0. Okay, so now let's think. Could we define this by a power series? So if this was a power series, well, a0 would be f of 0 would be 0, right? So there's no constant term. It starts with the x term. So if it was given by a power series, then what would the derivative be? Well, the derivative would be a1 plus 2a2x plus and so on, 3a3x squared, da, da, da. But the derivative is 1 over 1 plus x. And we know what 1 over 1 plus x looks like as a series because it's a geometric series. That expands as 1 minus x plus x squared minus x cubed, at least if the absolute value of x is less than 1. That's what you need for geometric series to converge. And now you take these two expressions and you equate coefficients. a1, the constant term has to be 1. 2a2 is minus 1, so a2 is minus a half. 3a3 is 1, so a3 is a third, and so on. And you see that actually our function, if it's defined by a power series, that power series has to be x minus x squared over 2 plus x cubed over 3, and so on. Okay, so yeah, there's a perfectly good power series. That was a typo, sorry. That was f of x, which is ln. If natural log was defined by a power series, that's what the power series would be. But there's kind of a problem here. This series has radius of convergence 1. Quite easy to see that because when you plug in x equals 1 in here, what's the series? It's 1 minus a half plus a third minus a quarter plus a fifth and so on, which converges by the alternating series test. When you plug in x is minus 1, you've got minus 1, minus a half, minus a third, minus a quarter, and so on, which diverges because, well, that's minus the harmonic series, which I'm sure you've seen diverges. So for x is 1 and minus 1, it converges or diverges. That forces the radius of convergence by our theorem about radius of convergence. It forces R to be 1. So it only gives a function on domain minus 1, 1. So we only get, using the power series approach, we only get a function natural log x on domain, let me see, I think that would be domain 0, 2. But this definition, the one that we started with, had domain 0, infinity. So somehow this is not a good approach, because it doesn't give us a definition of a function with the right domain, whereas this approach as an integral did that. And so this is just the way of things. The power series approach works best for some functions and not for others. For other functions like natural log, you have to come up with some other way of defining it, and this integral method is really the best definition for natural log. Okay, let's do one more example today. So this is really my favorite example of a power series. So this is again Isaac Newton. He did so many things in this period. This is that same little period of 2 or 3 years, 1665 around about. So the example is something called the binomial series. So let me tell you, well, I guess we should maybe just remind a little tiny bit about the binomial theorem. The classical one. So this is when you have a natural number 0, 1, 2. And the classical binomial theorem tells you how to expand 1 plus x to the power alpha just by foiling out. And it tells you it's the sum as n goes from 0 to alpha choose n, x to the alpha, where alpha choose n here, this is the binomial coefficient. From Pascal's triangle. Right, so these are the numbers. I'm not ever telling you this quite precisely enough, but this is something that I'm sure you've seen. Okay, so this is what we're generalizing with the binomial series. So to do this, we need what's called the generalized binomial coefficient. So here alpha is any real number, not just a natural number like it was coming from Pascal's triangle, but any real number, positive, negative, fractional, irrational, anything. And n is going to be a natural number. The generalized binomial coefficient, alpha choose n, here's the definition. So you take the number alpha and you subtract 1 and you subtract 2. And you keep going and you multiply these all together. And you stop at alpha minus n plus 1. So here there are n terms being multiplied together. And then you divide by n factorial. In particular, alpha choose 0 is just 1 always, because that would be the empty product, and empty products are 1. So let's see, why are they called generalized binomial coefficients? Well, there's a little lemma which says that alpha choose n, I guess it's alpha minus 1 choose n, plus alpha minus 1 choose n minus 1. This is equal to alpha choose n. And I guess we've got to prove this. So it's a simple identity. I'm just going to take the left-hand side and I'm just going to calculate. So the left-hand side is alpha minus 1, choose n. So you take these guys and you subtract, and it's going to end at alpha minus 1 minus n plus 1, which is there. And you take alpha minus 1, choose n minus 1, which goes like this, and it's going to stop one term earlier over n minus 1 factorial. And let me see, I think I need to stick an extra n here and an extra n here, because then I can put them all over a common denominator. So the first one gives me alpha minus 1, alpha minus 2, alpha minus n plus 1, alpha minus n, right? That's that first term put in there. And then the second term put in there, that's this. Oh, actually, it's most of the same term. So why they're going to have a lot in common. So I'm going to factor out all the common stuff. And then in that second term, I've just got n left, right? So there we go. But in the square brackets, that's just the number alpha. So that's all I've got. I've got that over n factorial, which is alpha choose n, which is the right-hand side. Okay, so just a silly bit of algebra to prove that identity. This identity, when alpha is a natural number, is the Pascal triangle recursion. Remember, to get the next number in Pascal's triangle, you take the two above it and you add them together. That 4 is 1 plus 3. That 6 is 3 plus 3, and so on. That's exactly the recursion to build these binomial coefficients in Pascal's triangle when alpha is a natural number. So this proves that when alpha is a natural number, the generalized binomial coefficient is the usual one from Pascal's triangle. Okay, and then once we've got these generalized binomial coefficients, we can consider what's called the binomial series. So here's the series. It's the sum as n goes from 0 to infinity, alpha choose n, that generalized binomial coefficient x to the n. And what I want to do is investigate this series. I'm going to call it something. I'm going to call it f of x. So let me see. I'm just going to kind of just do a little bit of work now to kind of go through this theory. So let's show that r, the radius of convergence, is 1. Actually, I'm going to show that it's greater than or equal to 1. That's good enough for me. It's usually 1, but let's see. If alpha happens to be a natural number, then actually alpha choose n is 0 for n bigger than alpha. That's because in that case, if alpha happens to be a natural number, n is bigger than alpha, well, that one of those terms in that product is going to be alpha minus alpha, which is 0. So that product's 0. And in that case, the infinite sum just collapses just to the finite sum. Sum as n goes from 0 to alpha, alpha choose n x to the n, because after the alpha term, you're just adding up a whole load more zeros. That's exactly the guy that features in the binomial theorem, the expansion of 1 plus x to the alpha when alpha is a natural number. So in that case, when alpha is a natural number, it's just a finite sum, and so of course it converges for every x. So the radius of convergence isn't 1 always. It depends on alpha, and when alpha is a natural number, the radius of convergence is infinity. Actually, it turns out in all other cases, the radius of convergence is 1, but I don't really care. I'm just going to show that it's greater than or equal to 1, and for this I'm going to use the ratio test to show the series converges if the absolute value of x is less than 1. So let's kind of go through this. It's not really a big deal, but I haven't reminded you very much of the ratio test, but let's do that quickly. You take the n plus 1th term and the nth term in the series, and you divide them, and you look at the absolute value. And what you have to do is you have to show that as n goes to infinity, this converges to some number less than 1. So it's a bit of a calculation. Let me try and do it. So the numerator is this binomial, this generalized binomial coefficient. And then it's that over n plus 1 factorial, x to the n plus 1, and the denominator is another one, except it stops one term earlier, x to the n factorial, and I'm taking absolute value. But most things cancel, so I really only need the alpha minus n and the x and the n plus 1. And if I divide top and bottom by n, it's alpha over n minus 1 over 1 plus 1 over n and an absolute value x. But as n goes to infinity, that goes to 0 and that goes to 0, so this goes to 1. So that overall it approaches x as n goes to infinity. Providing absolute value of x is less than 1, then it converges to something less than 1, and so the series converges, and that checks what I wanted. So this series gives a well-defined, indeed differentiable, function on the domain minus 1, 1. Because I'm only looking at this series on that domain now. Okay, so now I'm going to calculate the derivative. It's the term-by-term derivative by the general theory of power series, so that's n alpha choose n x to the n minus 1. Okay, I've got to do a little bit of calculating. Let me just remember that alpha choose n is alpha minus 1 all the way down to alpha minus n plus 1, and then we're over n factorial x to the n minus 1. And so look, I can cancel that n with that and just leave an n minus 1 factorial. And actually I'm going to do one more thing. I'm going to let n prime be n minus 1. I'm going to do a little substitution in that sum. So instead of summing as n goes from 1 to infinity, when n is 1, n prime is 0. And then what have I got here? I'm just kind of simplifying this thing. I'm going to pull out an alpha. I'm pulling that alpha out the front. And then what I've got left with here, that's alpha minus 1 choose n minus 1. But n minus 1 is n prime. And x to the n minus 1 is x to the n prime. So that's done that little substitution. It seems a bit silly now to call it n prime. Let's go back to changing that dummy variable to an n. Okay, great. So that's the derivative. And now I'm going to do one clever thing, which is I'm going to look at 1 plus x, f prime of x. Well, it's not that clever if you know where we're headed, but I haven't told you where we're headed, so this might seem like an unexpected thing to look at. So I've got to times that by 1. So there's our series. And I've got to times it by x and add together. Okay, that's great. So now I'm going to do one more substitution. I'm going to change this variable n again. I'm going to let n prime be n plus 1 and go through the stuff that I just went through. And it transforms into that when you go through those steps. And now I'm going to gather those two terms together because they both involve x to the n. So I'm actually using the limit laws in there in putting those that sum of infinite sums into one infinite sum. So there's a little bit of theory going in here. Secretly, it's some limit laws being applied. But now in those two brackets, I've got that identity from our lemma, this Pascal's recursion going on. So this is just alpha choose n. So this is the lemma that I just proved. And that is alpha f of x. So what I've just done is I've shown that f of x satisfies this differential equation. Okay, so I'm kind of turning around the philosophy from before. From before I said if you have a differential equation, you should view it as being a recursion for a power series. But here I'm going the other direction. I've started with this binomial series, I've started with this power series, and I've just proved that the function defined by this power series satisfies this differential equation. Now what I'm going to do is I'm going to solve this differential equation in a different way to actually reveal what function this f of x is in more classical terms. So what we've just shown is that the function defined by this power series on domain minus 1, 1 satisfies the differential equation 1 plus x f prime of x is alpha f of x. And of course, f of 0, when you plug in f in 0, you get 1. So now we're going to solve this by separation of variables. To work out what function f of x is. Okay, so let me switch to Leibniz. So this is 1 plus x dy by dx is alpha y. So I'm trying to separate variables, which you can do, alpha over 1 plus x dx, and then you put integrals plus c. Okay, so then we've got to integrate these things, but we can. This is natural log of y. This is what alpha natural log of 1 plus x plus c. But when x equals 0, y is 1. So on the left-hand side, you've got ln of 1, which is 0. When x is 0, that's 0. So that shows that c is 0. So actually, I've got the ln of y is, let me use laws of logs. And exponentiate y is 1 plus x to the alpha. So this proves the theorem the series, well, let me just write it really succinctly. For any real number alpha, 1 plus x to the alpha, that's our function f of x, it's equal to this binomial series, generalized binomial coefficient x to the n, on the interval minus 1, 1. So that is the Newton's binomial theorem, which generalized the binomial theorem when alpha is a natural number to the case of any real exponent alpha. And so this is kind of really an amazingly important and wonderful series. I don't know. So there's a question about this on the homework this week, so I don't really need to go into this in any detail. But for example, if you take alpha to be minus 1 and you change x to minus x and you calculate those generalized binomial coefficients, you find that this recovers the geometric series. I think I might get you to calculate that on the homework, so I won't go into it in any detail here, but the first term's a half, and then I think you get minus an eighth, and so on. I'm not gonna, I think the next one's probably a 16th. Let's see if I got that right. This would be, so that we're doing half choose 3. That generalized binomial coefficient. So let's calculate. So that's alpha minus 1, alpha minus 2. I've got 3 numbers multiplied together, then I've got to divide by 3 factorial, right? So I've got a half times minus a half. And then the next one we've got minus 3 over 2. And I'm dividing by 3 times 2. But the 3's are going to go. And it looks like I've got 1/16. Yes, I got it right, and so on. So you could use this to calculate square roots. For example, plug in x. I can't plug in x equals 1 because this has only got radius of convergence 1. You need to plug in something less than, well, maybe you can plug in x equals 1. I'm going to let you ponder that a little bit. Okay, so that's an amazing thing, and I think it's the last big theorem of Newton that I'm going to show you, this binomial series, and then we're going to kind of jump a little bit ahead in history. I think I'll just write this down and stop. I'm not going to really do anything about this, but I'm sure you've heard that I've been using the word power series. Probably you're more familiar with calling these Taylor series or Maclaurin series. So let's just write down Taylor's theorem. So this says that if you actually have some function which is infinitely differentiable at x equals 0, and you let an be the nth derivative at 0 over n factorial, this formula we've been seeing from these power series, Taylor's theorem tells you that actually the function f of x, the value of f at x, is equal to this polynomial, which is called the nth Taylor polynomial. Plus some error. Right, so this is a very key theorem when you're trying to calculate a value of a function by approximating it by a polynomial. It's saying the function equals the polynomial plus some error, and Taylor's theorem tells you what the error is. It says the error is, so you go one more derivative over n plus 1 factorial, except it's not evaluated at 0, it's evaluated at t, x to the n plus 1, for some t with absolute value less than that of x. And so probably you played with this error formula in your first calculus course. You can use this to come up with good bounds for the error, and in that way you can get very good estimates for things like exponential functions or trig functions or something like that. This is not going to be in any way important for us, but I've been calling these power series all along, and they were certainly, Newton was using them. You're probably used to calling them Taylor series, and you've seen this Taylor theorem with this Taylor remainder form. So I just wanted to write that down to make that link. Of course, Taylor was another English mathematician a little bit after Newton. But this is really this point in history where I'm now going to move away from Britain and British mathematics following Newton, and we're going to move to Europe and start talking about Leibniz and Leibniz's students. So this is kind of a good historical moment to make that shift.